Welcome back to our course on abstract algebra. In this video, I'm going to follow up on our previous video where we defined group, and we're going to look at some very basic properties of groups. Just as a reminder, this is our definition of group, a set with a binary operation star that satisfies that star is associative, that there is a neutral element, and there are additive inverses. And if in addition, if the operation is commutative, then we say it's a commutative group. But this is the very basic definition and axioms of group. So here are some properties that are just very useful for groups. First of all, and we proved this in the previous video, is that the identity element, the identity or neutral element in a group is unique. That we have proved, so I'm going to put a check mark right there. Then we also proved that inverses with respect to the operation star are unique. And we also proved this in the previous video. What else can we prove? 3, if you want to know what is the inverse of a product, then we have a formula for that. Then the inverse of A star B is B inverse star with A inverse. I'm quickly going to stop using star like this all the time, so I will write that AB inverse is B inverse A inverse to denote the same thing. So we're going to prove this. How do we prove this? What I want to show is that this expression works as an inverse. So I just want to show that it has the properties of an inverse for A times B. So what we need is that if this is, I don't know, T, I want that AB times T is the same as T times AB is the identity. Okay, so we can check that. So how much is AB times B inverse A inverse? I need the associativity here to write this as A times B inverse A inverse. Then I'm going to use the fact that B inverse is an inverse, and this is A E A inverse. And then A times E by associativity, that is going to be, let me just actually use associativity like this. And A times E is A, and A times A inverse is E because A inverse is an inverse. And similarly, I can do B inverse A inverse times AB. I can write this as B inverse AB, and that is going to be B inverse EB, which is B inverse B, which is E. And that checks that this is true. By the way, we do need to check both that it is an inverse on the left and on the right, because there are some sets where something can be a left inverse but not a right inverse, or a right inverse and not a left inverse. So we need to check both. Similarly, we can check that the inverse of an inverse is itself. So how would I check this? So if I call this, this T, for the inverse of a inverse, I want to check what is the inverse. Is going to be some T such that A inverse times T and T times A inverse gives me the identity. So I have to check those two conditions. And I can see that, A inverse times A is by, definition of inverse, this is the identity, and A times A inverse, that is the identity. And therefore, this tells me then that the identity or the inverse of the inverse is the element itself. So that checks out. Okay. So the inverse of the inverse is itself. Next, I want to show that in a group, let A and B be elements of a group, then the equations AX is equal to B, which these, let me just write it with the star. So the equation A star X equals B, and the equation X star A equals B have unique solutions. So an equation in a group, a linear equation like this, it has a solution, it has a unique solution. So let me first show you. So suppose we're trying to solve AX is B. Then let X be, it's going to be A inverse times B. Then I can check that A times A inverse times B is the same as A inverse times B. That is E times B, which is B. So it works. So it is a solution, and it is the unique solution, because suppose I have another solution, AX prime equals B, then I can multiply by A inverse on both sides, and I can simplify this to be A inverse AX prime, which is EX prime, which is X prime. So what I get is that X prime is the same as this, which was X, and therefore X is equal to X prime, and there is only one solution. And you can do similarly for the other type of equation. For this one, that there's a unique solution for X A is B. The solution is that it has to be B A inverse is the unique solution. And of course, here I am not assuming commutativity, so that's why you have to do a proof for both and never assume commutativity in any way. Okay. This one, by the way, is related to what we saw in the Cayley graphs. In Cayley graphs, we saw that every row and every column of a Cayley graph had a unique every column and every row of a Cayley graph of a Cayley table had, for example, in Z modulo 4 Z under addition, we had plus and 0 1 2 3 0 1 2 3. We had 0 1 2 3 0. Oops, this is a 1 1 2 3, and then 2 3 0 2 3 0 1, and 0 1 and 2. And what we notice is that every row has all the numbers without repetition, and every column has all the numbers without repetition, but in different orders. And why is that? Why couldn't there be a repetition? Because if there was a repetition, if we had a group G star and I had a table with some G in here, and there was a repetition where there was twice an H and an H, what that would mean is that there is an X1 and X2, I guess, such that X1G is H and X2G is H. But that would say that these are two solutions of xg equals h, but however, that is a contradiction because there's only one. There can be only one such solution. There is a unique solution. So the upshot of that is that in a Cayley table, each row and column contains every copy, every element of the group without repetitions. Okay. The last property I wanted to talk about is cancellation laws. So let A, B, and C be elements of G such that AB equals AC. Then B equals C. So it turns out we can cancel out in a group. And why is so? Because if I have, so suppose that AB equals AC, then I can multiply both sides because A is in G implies that there is an inverse element, and therefore I can multiply both sides by A inverse, and this side will be B while this side is C, and therefore I get what I wanted. So as an example of this, I will say that, for example, in Z modulo 6Z under addition, we have things like 2 plus 3 is congruent to 2 plus 9. And that implies that, well, that 3 is also congruent to 9 modulo 6. I can cancel out the 2 that is adding on both sides. And those two are true equations. However, under multiplication, we have to be careful because 2 times 2 is congruent to 2 times 5. 4 and 10 are congruent modulo 6, but 2 is not congruent to 5 modulo 6, meaning that I can't cancel out these 2 and that 2 and expect that 2 is going to be congruent to 5 modulo 6. What happened? Why is this not working out? Well, it's not working out because this is a group. We know that Z modulo 6 under addition is a group, but this is not a group. So while this applies to this example, this does not apply to this example because this is not a group. 2 does not have a multiplicative inverse. So I cannot cancel out that 2 in this equation over here. All right. So in the next video, we will talk about subgroups.